Many liquids are essential in our daily life. They may include water, beverages, dairy products, chemicals, acids and bases, or pharmaceutical products. The quality of these liquids is determined by their chemical and physical properties. To assess these properties, various principles of measurement are used. One of these principles is the measurement of electrical conductivity. Let's start with a closer look on why liquids are conductive. The electrical conductivity of a liquid arises from the dissociation of soluble salts, acids, and bases to form positively charged cations and negatively charged anions. These ions contribute to the charge transport in the electrical field, and thus to the current flow, just like electrons in a metal. In 1869, German physician Friedrich Kohlrausch developed the first conductometer for electrical conductivity by using an alternating current to measure electrolytic resistivity for the first time. The physical unit of electrical conductivity is Siemens per meter. To determine the value, the so-called conductive and inductive measuring principles can be used. In case of the conductive measuring principle, two electrodes are positioned opposite from each other. An AC voltage is applied to the electrodes, which generates a current in the medium. The cations move to the negatively charged electrode, while the anions move to the positively charged electrode. The more free charge carriers the liquid contains, the higher the electrical conductivity and the current flow. A 10% acid, for example, is a very good conductor because it contains many ions that transport the charge. In contrast to this, pure and ultra-pure water are bad conductors because they contain only few ions. If, however, the ion concentration becomes too high, the Coulomb force increases. This electrostatic force leads to a mutual repulsion of the ions and thus a reduction of the current. The effect is called polarization and occurs with highly concentrated media. The electric resistance, or its reciprocal value, the conductance, is calculated from the measured current according to Ohm's law. To derive the specific conductivity from the conductance, the so-called cell constant must be determined. It is based on the geometry of the electrode arrangement and reflects the distance of the electrodes in relation to their surface. It varies depending on the electrode design and influences their suitability for different areas of application. Conductivity is also dependent on the medium temperature. Therefore, the temperature is measured in parallel and the conductivity values are referred to a reference temperature of 25 degrees Celsius by the transmitter. Conductive sensors have a simple design and are highly sensitive, which makes them suitable for a wide range of applications, from ultra-pure water to drinking water and more. The inductive measuring principle uses the inductive conductivity sensor. It contains an electromagnetic transmission and reception coil in a protective plastic coating. An alternating magnetic field is generated in the transmission coil, which induces an electric voltage in the liquid. This causes the positively and negatively charged ions of the liquid to move and generate an alternating current. This current again induces an alternating magnetic field, and thus a current to flow in the reception coil. The intensity of the current depends on the number of free ions in the medium. It is evaluated by the transmitter, and the conductivity is calculated. The advantage of inductive conductivity measurement is the galvanic isolation from the medium. Polarization effects cannot occur, and the measuring principle is insensitive to soiling. The conductive and inductive conductivity measurement by Endress and Hauser enables precise control of water treatment and cleaning and rinsing processes, for example in the food, life sciences, and chemical industries. For further information on liquid analysis and the latest conductivity sensor generation featuring MemoSense technology, visit the Endress+Hauser YouTube channel or www.endress.com.